What's going on, YouTube? It's me again, and I'm back with another topic review, vlogging and documenting my learning journey at the Flatiron School. So, if you're new here, if you've never seen any of the videos on my channel or in this series, I'm currently enrolled as a student in the data science program at a coding bootcamp called the Flatiron School. Learning a lot more than just coding, so that's part of why I like to, or wanted to start doing this vlogging series, was because I think calling Flatiron, at least the data science program, I can't speak for the software engineering program they also offer, but in the data science program at least, we're learning a lot more than just coding. What we're really learning is data science, like statistics and calculus and that sort of stuff, and then we're just kind of like the icing on the cake is how to do those things with code, right? So I'm in phase 3 of 5. This whole phase is kind of like the fundamentals of machine learning, and what I studied for this module, there's about 10 modules in each phase, is some things called gradient descent, and we also went over derivatives a little bit, which is, if you're familiar with calculus at all, that ought to you ought to be right on beat with this episode. So as usual, I've got my one pager. This is the front. I need to fill this top out a bit because there were actually some topics in this module that that kind of refers back to topics from other modules. And the bottom half here, which is like where I just list, there it goes, kind of the major ideas of the module. You can see there's not a lot written here, but like the last one, it basically filled up the whole back of the page, which is where I write out all the details about it. These two things that you basically see here are derivatives and gradient descent. Sorry, I've got the background blur on because you can see my laundry in the laundry chair over there, so I just don't want to broadcast my whole messy room to the world. But yeah, so last video I did went over an hour, and that was way longer than I wanted this to be. I want to try to keep this down to 15-20 minutes if possible. So I'm gonna run through this a little bit quicker than I did last time. So if you have any questions or anything about this, leave a comment or DM me. I'd love to expand on it later. But with that said, the point of this video is more of an exercise for me to make sure that I understand the stuff that I supposedly learned, because I think it helps a lot to figure out exactly what about something you don't understand, why you don't understand it. You realize those things in the process of sort of teaching them to others. I say the word teaching. This isn't exactly educational as much as informative, but you get the idea. So, with that said, let's go to our Jupyter notebook. So, we're in Module 23. The first thing that we are going to talk about is derivatives and just a little bit of calculus around that. And then we're going to talk about how the derivatives are used in this optimization algorithm called gradient descent. And then at the very end, I'll show you a code snippet of basically how this is all applied in Python. So, to begin with, derivatives. I don't know how to. Oh, I get it. There we go. We're good. See, I did it in the last notebook where it shouldn't say one cell hidden anymore when I uncollapse this, but it still does. But it's not in the way of anything, so it's okay. So a derivative is just a fancy word for the instantaneous rate of change of a function, or in other words, the slope of a function, the rise over run. In other words, it's not exactly rise over run when you get into multi-dimensional derivatives, but if you're only dealing with one variable and one constant, so a y and an x-axis, you can think of it pretty much as the slope of a line, right, or the slope of a curve, rather. So if the example that Flatiron used a lot was is thinking of rate of change in terms of time. So you can imagine that as the time frame that you're measuring across 3 seconds or 2 seconds or 1 second or half a second or whatever, as that approaches 0, the derivative, the rate of change of any given function, is going to approach some limit. So let's say the slope is 4.1 some weird like non-repeating decimal point. You'll notice that as you bring your your time frame that you're measuring closer to 0, the derivative is going to go from 4 point something to something, 4 point something that's like a little smaller and smaller and smaller, and it's going to approach 4, and so you call like 4 the limit of your derivative essentially. So we'll start with the basics, talk about derivatives of non-linear functions. It's pretty straightforward. It's literally just like your rise over run for a function on when you're talking about linear functions, at least. So the way we notate it here, so we have like f of x, right, represents like this line here, and the derivative of f of x is notated as f primed of x. That's what that little like apostrophe right there basically means, is primed. So this delta notation you see here, that basically just represents change. So that's just a more concise way of representing this information right here. We have y2 minus y1 over x2 minus x1. That might sound familiar if you took like any math at all in high school. And so you can see here we have these 2 points on this graph. We have our point 1 and point 2. So we have x1 and y1, x2 and y2. And to get the derivative of this function, we just take the difference between our these two vector points basically. And if you paid attention or watched it all like the last video, you'll know that a set of numbers is a vector, so that's why we can call these vector points basically. So there's a few rules for calculating derivatives, because did I mess up my I did. This should not say rules for calculating derivatives. This should say something like derivatives of non-linear functions. And all that means, like non-linear, is that it's not in a line. So you see we have like some curved lines here. And this is where like your limits come into play. So say I want to know like what the rate of change is. Let's say the x-axis here represents time, right? And maybe your y-axis represents speed, right? So this curve would like represent acceleration. So you want to know like what the rate of change is at a specific point on the graph. So from second 2 to second 3 or something, like you see the dotted lines here. You can draw a straight line there, and you can do your y2 minus y1 over x2 minus x1, but that line is actually going to be shorter than the actual distance covered by the curve here. You can see. So I kind of think of that of like how plane wings work, how they generate lift, is because it's longer distance there has to travel over the wing than under the wing, and yeah. But don't like think on that too much. That's just like a weird connection I make in my brain. So what we do is, so this is like the time frame that I was talking about. Imagine like the time frame that you're measuring approaching 0. That's like this distance between these two x values as they approach 0. So that's why you have to, when you're dealing with nonlinear functions, calculate like the limit of the derivative, because you can't really calculate like the derivative itself. But you can get close enough that it's like useful to do like discover things from your data. You can get close enough to do that with calculating the limit. And if you know anything about calculus, there's this common theme in calculus of like as things approach infinity or as things approach 0 and become infinitely smaller, infinitely bigger. So the derivative is very closely related to integrals. If you know anything about calculus, derivation and integration are kind of two sides of the same coin, so to speak, or inverses of one another. Anyway, so how you calculate that is in calculus, the derivative of a function of a nonlinear function is defined as this here. So you have the function of x plus the change in x minus the function of x, which is going to be some number depending on whatever x value you're calculating at. And you divide all that by the change in x. And it's important to note all this right here, the f of x plus delta x minus f of x. that can all just as easily be, I mean, that is equal to delta y. So like up here, we have delta y over delta x. This is literally that same thing, only y is a constant and we have x as a variable, and so we're trying to solve for y, right? So we don't already have it, so we can't plug it into our formula. So we have this formula instead. And very smart math people at some point or another figured out that this is equivalent to delta y. So that's nonlinear derivation. So you can kind of see here what we mean by as x approaches 0, right? So we have x1, x.1, x.01, x.001, and we're going to get slightly different slopes. Or what your derivative is basically is the slope of this dotted line that you see here. And if that, the goal is that that line, is tangent to the curve, right? Meaning that it just touches it at one point. So you can essentially calculate like what's the rate of change at second 2, instead of like kind of estimating what's the rate of change between second 2 and second 3. So that's nonlinear derivatives. 11 minutes here. We're doing all right on time. And I do actually have to be somewhere, so I do actually need to get going. So now rules for calculating derivatives. The power rule basically is, don't worry about like why or how or whatever, but basically if you have an exponent, or if your predictor variable, right, has an exponent, all you do is you multiply, we'll call x our parameter here, you multiply the exponent by the parameter, right? So you bring it down here, you can see we got x2 and then 2 times x2 minus 1. So that's more generally notated here. You have x to the power of r, and the derivative of that would be r times x to the power of r minus 1. So likewise, we have x squared. The derivative of that is 2 times x squared, x to the power of 2 minus 1, which is really just equal to 2 times x, because anything to the power of 1 is simply itself. That's some rule. There's some name for that law or something somewhere. Your constant factor rule is a little weirder, but basically it just states that if you have a coefficient to your parameter, you multiply that coefficient by the parameter. So then if you have like this example here, you have your coefficient times x squared, you find your derivative for x squared, or x to the r, whatever that is, and then you multiply your coefficient by that. So it sounds a lot more complicated than it really is. It's just PEMDAS, basically. So moving on, we got our addition rule. This is actually pretty simple. This basically just states that if you have a function with multiple terms, and by term we mean any like single unit that's separated by a plus or a minus, then so that it's important to note this doesn't necessarily count, I guess, with like multiplication or division. Things get a little more complicated with that. But where you have multiple terms like this, where so this could even be like 4x over 3, and that's still considered like a term because then it's separated by the minus sign, right? You find the derivative of each term individually, and then you sum it all up at the end, right? That's basically all the addition rule is you derive each term individually and then sum them after you've already derived each term. So this is another just like neat visual kind of like showing like your tangent lines along your nonlinear function here. And you can see that this is showing you like what the slope is. So like our green line here, the slope of that, for every 4 units that it goes up, it moves over 1. And likewise for slope of, I got my colors confused. So this is like negative, right, because it's going down. Green and red are positive because they're going up. Pretty straightforward visualization there. So minima and maxima. So you can imagine, like, there's not, like, why would you, like, want to know, like, the derivative of any just random point um, on the function? You don't. What you actually want to know is where the minima or the maxima. So if this is an if this function was negative, it would be an uphill uh, hump or what have you, and the maxima would just be the same thing. It's the peak. It's the most extreme point of the function before its sign changes, right? So this half of the function, basically, the sign is negative. This half of the function, the sign is positive. Maybe don't think about it like that because it's all one function, so it only has one sign. But the slope, any derivative on this side, on this half of the function, would be negative. Any derivative on that half of the function would be positive. So the big thing to understand here is that whatever the minima of your nonlinear function is, that is going to be the x-intercept of your derivative of that function where x equals 0. So did I say that right? Sorry, no. The minima or the optimum, minima or maxima, the optimum of your nonlinear function is going to be, the x value at least, is going to be the same as the value for x when the derivative equals 0. So when your derivative function, when f prime of x equals 0, whatever value of x makes that derivative function equal to 0, that is going to be the optimum of your nonlinear function, or the minima or the maxima or the peak, in other words. And so all that math is right here. Like I said, I'm trying to like not just kill a ton of time on this like I did last time. So you might imagine with large data sets and more complex variables and that sort of thing, it's, you know, here we can pretty much just look at the graph and like tell what's going on. However, in some, you know, real world data science use cases, you're going to actually want to mathematically be able to calculate this. So imagine something that's in like 3, 4, 5, 6 dimensions. When you have 3, 4, 5, 6 different predictor variables, you're not going to be able to visualize this. So you have to do it mathematically. So gradient descent, now this is bugging me. Is an optimization algorithm used to find the values of a function's coefficients that minimize the related cost function, right? So our cost function is always going to be this, what's it called? Nonlinear function right here. For our purposes, our cost function is coming from the residual squared errors of various inputs of our regression line as we're trying to find the best fit for our regression line. So this is a way to find, say you have like your scatter plot and you have some regression line and you want to figure out what is the regression line with the least residual squared errors. So the sum of the gap from the observed data points to the predicted data points. You want to find where your RSS value is the least, right? And so gradient descent is a way to figure that out without doing more math and more computation than you have to do, right? So I should have included a better visual for that here, but we'll get on with ourselves. So you begin with a regression line with your best guess for M and B. So B is like your y-intercept. It's your y-intercept where x equals 0, right? And M is the opposite of that. Basically, it's your x-intercept where y equals 0. So you calculate the residual sum of squares for that regression line. And I've done that in like past videos before if you're like really wondering what that is. You adjust your M if you're trying to adjust along the x-axis, or you adjust B if you're trying to adjust along the y-axis. You recalculate your residual sum of squares, and you repeat this process. And you select the values for M and B where your RSS is the least. So the change in output based on the change in input of M or B, right? So the change in your RSS based on how you change M or B is the cost function, and that's pretty much always going to appear as a curve like this. right? So I should really do more bullet points and like write less paragraphs. So if the slope approaches 0 on the y-axis, i.e. the slope is negative, the next step should move towards infinity, or away from 0, in other words, right? And vice versa. If the slope approaches infinity on the y-axis, then the next step should move towards 0, right? Fancy or mathematical way of saying, if the slope is going this way, then you want to move to the right. If the slope is going this way, you want to move to the left. And again, when you start working with higher dimensional data sets, that's not something you can really visualize, so you have to be able to do it mathematically. So, sorry, I'm going really fast. I'm like losing my train of thought. The general procedure to find the ideal m is, or the coefficient value, is as follows. You randomly choose a value of m, just like earlier we randomly began with a regression line. You select some step size, which is notated with the Greek letter eta. Then you update m with this formula here. M equals eta, your step size, times the slope, your derivative, at whatever point you selected for m, right? And this little code snippet here is just kind of an example of what that would look like in Python. So let's talk about higher dimensional gradient descent. So I'm going to link this notebook in the description so you can really dig into this calculus here if you want. But what all this is saying is basically that when we have higher dimensional functions that we're dealing with, we can't take the derivative at any one given point. So what we have to do is take the derivative, if you imagine like you sliced it this way and you sliced it this way, we take the partial derivative of like one variable. So if I want to find the optimum for x on this graph here, I would do that by treating y as a constant when I do my algebra to actually calculate the derivative. So I would find the optimum for x, and then I would find the optimum for b, and you kind of keep doing that back and forth until, for this function at least, you're going to end up kind of like right in the center here. So that's the idea, is when you're dealing with multiple predictor variables, to put it in like data analysis language, you're going to have to find the partial derivative of each one of those predictor variables while treating the rest as constants, and you do that individually for each one, and you kind of keep iterating through that until you find the combination of those like partial derivatives where your RSS is the least. So yeah, this is how that's represented in calculus. Like I said, I'm gonna link this in the description, so if you really want to dig into that, it's all like right here for you. Notice that now we're like defining our referring to our function as f of x and y. Later on, you'll see this represented as f of x1 and x2. When you see that, just know it's basically like x and y. It's just like, so you can imagine like this would be x1, this would be x2, and this would be y. It's just like maybe for some people an easier way to like think about it. So with code, this is how you would sort of like apply that calculus to update your m and your b values as you go through this. It's important to note that your b value is going to be an intercept versus your m, when you're dealing with multiple predictor variables, is actually going to be an array or a vector of parameters. So how do we do that in code? So we're importing, I don't know why I imported matplotlib, actually. I didn't actually end up running any visualizations here. But anyway, so we import NumPy, at least, because that makes it really easy to do cool math stuff in Python. Setting a random seed here, just so I was like, you don't have to set a random seed if you're trying this out. It's just, if you don't know, it's going to set things so that you're going to get like a falsely random output, but you're going to get the same output every time you run the cell. If you don't set a seed, you're going to get like an actually random output. Not random enough for like security purposes, but random enough for what we're doing here. Pseudo-random, technically. Point being, don't encrypt like your passwords with NumPy or something like that. Yeah. Anyway, so now you see here we have our x1 or x2. Those collectively represent m, right? So m is x1 and x2 now. We're getting some random like y-intercept just to like start off with. We're defining our function and just kind of getting our data ready to be plugged into our function down right here. So this block of code right here is this calculus in code form, basically. So some things to note: you have your learning rate, which is like how big of a step you take every time you step to along your curve, right? So every time you adjust M or adjust B, by how much do you adjust it? That's your learning rate, and that's kind of like p-values and like confidence intervals, in the sense that like there's like some like broadly used and accepted like numbers, but there's not like a real like mathematical rule or law saying like it should be this according to like some other like condition of your data. So 0.1, 0.01, 0.001 are like pretty common. So you can imagine if you have a larger data set, your RSS value is going to increase. If you have like say like two regression analyses, one uses like a data set with 1,000 rows and the other uses a data set with 100 rows. The one with 1,000 rows might have a better fit regression line, but the RSS value is still going to be greater just because there's more data points that are being summed into that residual sum of squares. So to deal with that, because that doesn't necessarily mean you have a less fit line, it just means you have more data. So that's why we're multiplying 1 over the number of rows in our data set, basically, to kind of weight our output here. When we calculate our RSS, we're weighting it according to how much data we have in the data set that we're plugging in. Excuse me. So that is not represented in the calculus right here. That's we have this -2 here because we have 2 predictor variables. I think that's why. Don't quote me on that. But that's why we're dividing by -1 over n here. Is we're weighting our RSS according to how much data that we have. So this is the formula we just saw a minute ago right here. Yep. Where we're updating our b values and our m values, and basically what's going on here is we're iterating through every row in our data set, and we're finding our x and our y values at that like intercept point on the cost curve, and then we're calculating our RSS according to whatever the slope is there, and we're doing that twice, once for b and once for m, and each time we're treating the other as if it's a constant and not a variable, right? And then we update them according to the outputs. We're calculating our RSS here, and then we return this tuple. So we repeat that process 500 times, and this block of code alone right here, that's gradient descent. So we could run this 500 times, we could do this 1,000 times, 1,500 times, 1,000,000 times. It really depends on how much time you have and how much computing power you have. However many times you do run it, the final output of that using this algorithm is going to be the parameters that you want to use for your best fit line. So we have our b value here, our y-intercept, and our m values here, which remember we have 2 now, so that's why we have an array, a NumPy array right here. So these are the values we want to use for our y-intercept and our target variable and our predictor variables for our best fit regression line. When we plug this into our linear function that represents our derivative, and when we plug this into f primed, that is going to be the line that has the least residual sum of squares for the data that we did this analysis on. So long story short, gradient descent is a way of starting with some, so imagine like a scatter plot, and then there's some line going through it here. I really should have had a scatter plot included in this. But you can imagine as you rotate that fit line and you maybe translate it up, down, left, and right, that's going to change how well it fits the data. How well it fits the data is represented by the RSS, which creates this curve function here. And so looking at those two things together, we can, instead of calculating every single little point along this curve, we can take steps that are smaller and smaller and smaller and approach the limit, right? And eventually we find what our best fit line is, or at least something really, really, really close to it according to the limit, right? And gradient descent is an algorithm basically that will figure out how big are these steps to take without overshooting and kind of going like way down here, and also without calculating every single little infinite point along this line, because to calculate every single infinite point along this line, there's no computer in the world that is going to do that, and it's probably at some point the juice ain't worth the squeeze, so to speak. So sorry I kind of ran through this, but like I said, I'm going to link this notebook in the description like I always do. So if you really want to dig into this, or you want to dig in, test out this code yourself or anything like that, it's all going to be there available for you. Leave a comment if you have any questions about this topic or Flatiron as well. And yeah, so that's pretty much it for Module 23. I'm not doing this on behalf of Flatiron. I don't know that Flatiron necessarily knows that I'm doing this vlog. So a lot of this content and a lot of these code snippets and stuff, some of it's mine, some of it comes from Flatiron. So I just want to kind of put that disclaimer out there, that this isn't 100% my original work, and I'm not doing this on behalf of Flatiron. I just I'm having a great experience at Flatiron, and I want to share it with everyone. And it's also good for me to practice the things I learned by trying to explain the things that I learned to other people. So, that said, hope you guys have a great rest of your day or night or morning or whenever you happen to be watching this. And I will be back again soon with a topic review for Module 24. Take it easy.